Give the major product of each reaction. The first reaction is hydrohalogenation of alkene, and reagent is only HCl. We know that this is a Markovnikov addition. And first a carbocation forms. So first pi bond breaks. Pi bond will act as a base here and forms a new sigma bond with the hydrogen. And the carbocation forms. In Markovnikov addition, we add hydrogen to carbon with more hydrogens. If I call these carbons A and B, carbon A has 2 hydrogens and B has only 1 hydrogen. So I will add hydrogen to carbon A, and carbon B becomes a carbocation. This is a secondary carbocation. Does it undergo rearrangement? No, because if it undergoes rearrangement, it either becomes another secondary or primary. And in the next step, chloride will act as a nucleophile, attacks the carbocation, carbon with positive charge, and this is the final product, final major product. The second reaction, in the second reaction, reagent is HCl and peroxide. And we know that when we mix hydrogen halide with peroxide, mechanism of reaction will change. It's radical reaction, and product is anti-Markovnikov. So this is anti-Markovnikov addition, which means we add hydrogen to carbon with fewer hydrogens, carbon B. And we don't have to worry about the rearrangement or anything. We just have to add hydrogen to carbon with less hydrogens, carbon B, and nucleophile to carbon with more hydrogens, carbon A. And this is the major product of this reaction. In both of these reactions, when I added hydrogen to carbon A or carbon B, I didn't show those hydrogens because these are bond line structures. But you know that the hydrogens are there. For example, in the first reaction, when we add hydrogen to carbon A, there will be 3 hydrogens here, but we don't show it. Same thing here. For the second reaction, when we add hydrogen to carbon B, there are 2 hydrogens on carbon B. One of them is from HCl, the other one was already there. Reaction of alkene with hydrogen halide. We know that this reaction is Markovnikov, which means hydrogen adds to carbon with more hydrogens. Pi bond will act as a base. And if we call these sp2 carbons A and B, A has 2 hydrogens and B has only 1 hydrogen. So we should add hydrogen to carbon A. And this carbocation will form. This is a secondary carbocation because carbon with positive charge is bonded to 2 other carbons. When there is a carbocation, we have to check the possibility of rearrangement. A hydride shift from the left side converts this secondary carbocation to a tertiary carbocation. which is more stable. So this rearrangement will happen. And then in the next step, bromide will attack carbocation. And final major product will form. Give the major product of the following reactions. Okay, this reaction, again, reaction of alkene with hydrogen halide. I call the carbons A and B. We know that there are 2 hydrogens on carbon A and 1 hydrogen on carbon B. With hydrogen halide, the first step is pi bond will attack the hydrogen. And we know that this is Markovnikov addition. So we add hydrogen to carbon with more hydrogens, carbon A. Now this hydrogen, this carbon A will have 3 hydrogens, and carbon B will have 1 hydrogen and a positive charge. So this is a carbocation. It's a secondary carbocation. When there is a carbocation, we have to check the possibility of rearrangement. Here, a metal shift will convert the secondary carbocation to a tertiary carbocation, which is more stable. So this carbocation will undergo rearrangement. This is carbon B. After rearrangement, it will have a metal group, and that's carbon A. And again, I'm not showing the hydrogens which are bonded to carbons. In the next step, bromide will attack carbon with positive charge, carbocation. And the new sigma bond forms. And this is the final major product. If we use the same substrate, the same alkene, but we add peroxide to HBr, so we mix hydrogen bromide with peroxide. The reaction becomes anti-Markovnikov, and we don't have to worry about rearrangement. You just add hydrogen to carbon with fewer hydrogens, and bromine, the nucleophile, to carbon with more hydrogens. And this is the final product of this reaction. Give the major product for each reaction. All of these 3 reactions are hydration of alkene. So we are adding components of water, OH and H, to sp2 carbons of the double bond. The first one is reagent of the first reaction is H2O and acid. The first step, pi bond will act as a base, and a sigma bond forms between one of the sp2 carbons and a proton. And which one? Carbon with more hydrogens. This is Markovnikov addition. So a secondary carbocation forms. Then a metal shift converts secondary carbocation to a tertiary carbocation. And then H2O will attack the carbon with positive charge. And after deprotonation, final product forms. The final product is a tertiary alcohol. The second reaction is oxymercuration, demercuration. And we know that this reaction is Markovnikov. It's anti-addition, which means OH and H will add to opposite sides of the double bond. And there is no carbocation rearrangement because there is no carbocation involved. So the only thing that we need to do is to add hydrogen to carbon A and OH to carbon B. And again, I'm not showing the hydrogens which are bonded to carbons, but we know that there are 3 hydrogens bonded to carbon A and 1 hydrogen bonded to carbon B. And the last reaction is hydroboration oxidation. We know that this reaction is anti-Markovnikov addition, which means that hydrogen adds to sp2 carbon with fewer hydrogens, in this case carbon B. And nucleophile will add to sp2 carbon with more hydrogens. In this case, that's carbon A. We also know that this is a syn addition, which means that OH and H will add to the same side of the double bond, and there is no rearrangement because there is no carbocation. So we draw the molecule again. This is carbon A, this is carbon B. We add OH nucleophile to carbon A, carbon with more hydrogens, and hydrogen will add to carbon B. I'm not showing the hydrogens which are bonded to the carbons, but we know that there are 2 hydrogens bonded to carbon A and 2 hydrogens bonded to carbon B. So 2 hydrogens here and 2 hydrogens here. This reaction, alkene, is the substrate. Reagent is H2SO4 and ethanol. This is similar to hydration of alkenes with acid and water. But here, instead of water, we have ethanol. So the nucleophile is ethanol. Pi bond will act as a base and attacks the acid, and a new sigma bond forms between one of the sp2 carbons and proton. And this is a Markovnikov addition. So hydrogen adds to carbon A and carbon B becomes a carbocation. So this is a secondary carbocation, a metal shift, will make secondary carbocation a tertiary carbocation, which is more stable. And then ethanol will act as nucleophile, attacks carbocation, and after deprotonation of this oxygen, we get the final product, which is an ether. This is the final product of this reaction, final major product. Propose an efficient synthesis for the following transformation. So here we have to change the location of bromine. If we number the carbons 1, 2, 3, 1, 2, 3, we have to move bromine from carbon 1 to carbon 2. These type of transformations are series of elimination and addition reactions. For each elimination, we have to decide if it is Zaitsev or Hofmann. And for each addition, we have to decide if it's Markovnikov or anti-Markovnikov. To prepare this compound 2-bromopropane, if we go back one step, this is what we need. We need this alkene. Now, can we prepare this alkene starting with the substrate? Yes, we need a strong base like methoxide. Elimination reaction, E2, gives us this product. And in this case, doesn't make any difference if we use small base or bulky base like methoxide or tertiary methoxide, because this is the only possible product. And then in the next step, we have to convert this to the final product. So we want to add a hydrogen and a bromine. Hydrogen to one carbon and bromine to the other one. Now we have to decide if we want Markovnikov addition or anti-Markovnikov addition. When we compare the alkene and the product, you'll see that we should add hydrogen to carbon with more hydrogens, carbon 1, and bromine to carbon 2, carbon with fewer hydrogens. So this is Markovnikov addition, and we have to add HBr. The reverse reaction is also possible. We can convert 2-bromopropane to 1-bromopropane. Again, if we have this alkene, we can prepare 1-bromopropane, and first we add a strong base. Doesn't make any difference if we use small base or bulky base, because this is the only possible product. And then we have to decide if we need Markovnikov or anti-Markovnikov addition. When we compare the alkene with 1-bromopropane, you see that we have to add hydrogen to carbon 2 and bromine to carbon 1. So we are adding hydrogen to carbon with fewer hydrogens and bromine to carbon with more hydrogens. And this is anti-Markovnikov addition. So we have to use HBr and peroxide. Propose an efficient synthesis for the following transformation. Here we want to convert 1-butene to 2-butene. So in the reactant, double bond is between carbon 1 and 2. In the product, it's between carbon 2 and 3. So when we are changing the location of the double bond, we need to use a series of addition and elimination reactions. Again, for each addition, we have to decide if it is Markovnikov or anti-Markovnikov addition, and for each elimination, is it Zaitsev or Hofmann. And I'm going to use retrosynthesis again. I go back one step from the product to prepare that alkene. If I have this alkyl halide, I can prepare that alkene with elimination reaction. Now, can I prepare this? Starting with the substrate, the 1-butene. So I have to add a hydrogen and a bromine. We need HBr. But is this Markovnikov or anti-Markovnikov? When you check the reactant, 1-butene, and the product, 2-bromobutane, you can see that you're adding we have to add hydrogen to carbon 1, carbon with more hydrogens, and bromine to carbon 2, carbon with fewer hydrogens. This is Markovnikov addition, and we need HBr. Now we have to convert 2-bromobutane to 2-butene. This is elimination reaction. Is it Zaitsev or Hofmann? Since you want the double bond between carbon 2 and 3, we want the more substituted alkene. So this is Zaitsev, and we need a small base like methoxide. We can also convert 2-butene to 1-butene. Again, we need a series of addition and elimination reactions. To prepare 1-butene, if we have 2-bromobutane, we can make 1-butene. And what reagent do we need to go from 2-butene to 2-bromobutane? We need HBr, and since the alkene is symmetrical, we don't have Markovnikov, anti-Markovnikov. Either if we use HBr or HBr and peroxide, we get the same product. And then from 2-bromobutane to 1-butene, this is Hofmann product, the less substituted alkene, and we need a bulky base like tertiary butoxide.